All of you, and good morning, and welcome you all again to our third and final session of the workshop series of regression analysis. If I brief what we have discussed in the very first session, Dr. Chaturani explained the different models available and how we can choose the right model by exploring the nature of the data, and how we can run a multiple regression model. In the second session, actually, she took more time to describe the mediating variable, how we can test the mediator in a conceptual model with testing assumptions. I mean the goodness of the model. And the third session, final session, we will focus more on another important element, that is how we can testing a moderator. Right. So I hope she will clearly demonstrate how we can do in a correct way, proper way. So I cordially invite Dr. Chaturani to commence the session. Thank you.
Thank you very much, sir. Can you all see the screen?
Yes, we can see.
As Professor Lalit mentioned, we started with the regression analysis, simple linear regression analysis, and I explained the underlying concepts, assumptions and all. Then we moved to the multiple regression part, and we analyzed different types of multiple linear regression models, and I did discuss some of the modifications that we can do to models based on our data and based on the patterns we see in the error plots and all. And we discuss how to check the assumptions of the multiple regression models. Because in our approach also, even though we are dealing with constructs measured by several indicators, we sometimes use multiple regression in our analysis. That's why this area is very important for all of you. And we last session we discussed the mediator analysis, and I explained the meaning of the mediator variable and how to analyze it using Excel. And as mentioned, I mentioned in earlier sessions also, when you have mediator variables, moderators, especially when you have several variables together in a complicated model, you have to go with the structural model rather than going with multiple regression model. But when you have, most of times we deal with simple models as well, so we can go with regression analysis in those models. So today we are going to discuss the motivation analysis. I think most of you have a good idea about moderation, but here I am going to start. I'm going to give a brief introduction to what is moderation, and then we are moving to analysis. I'm going to do some examples with you, and you take your time and do the examples by yourself. I appreciate if you can ask your questions, right? Maybe after doing all the analysis we can discuss, but while you are doing analysis, you better raise your questions, and whatever the unclear points to you, you can discuss with me. First of all, let's see the moderation analysis. This is kind of a relationship that we categorize as a moderation. You can see here, X is the independent variable, Y is the dependent variable. We assume a relationship between X and Y, right? We assume actually X has some impact on Y, right? So this relationship is moderated by a variable called M. This is the moderator. It means that it's at different levels of mediator, this relationship can be variable. The meaning of moderator is this is a variable that specifies conditions under which a given predictor is related to an outcome, under which conditions this X variable relates to Y. Under which conditions this X variable relates to Y. That can be varied under different conditions. For example, if you look at the relationship between certain X variable and Y variable, let's say if you are giving a training to your employees and you want to know whether this training time, the time you spend on training affects their performance, right? You check the performance as the response variable, and your X variable is the training time, or it should be actually a continuous variable, right? So if you want to check this relationship, whether this affects this variable varies across different levels of employment. Let's say you are giving the same training to people who are qualified from science and people who are qualified from management, right? They all are managers at the same level, but the difference is they are undergraduate qualification, they are degree qualification, right? Their degree qualification, they may be coming from, these days, people coming from mathematics or science backgrounds, as well as people from management field are in the industry. So we can check the relationship between their training effectiveness, right? That means whether the time, the training you gave, and there is a effect of that training on performance of the employees. Then we can check whether this is different across their education qualification, right? You can group the whole respondents into two categories based on their degree qualification, science and other fields, right? So you can check this as their education background as a moderator, right? That is actually the condition. Let's say you found that people who are coming from commerce and other streams, they get more more relationship between these two. They are getting more effectiveness. This relationship should be stronger for that group, right? But at that analysis, actually, our moderator is a categorical variable. But sometimes we can check moderators which are not categorical, which are also continuous variables. So moderation implies an interaction effect. We are introducing a moderating variable changes the direction or magnitude of the relationship between two variables. Most of times we are dealing with situations where we get different magnitudes of these relationships. For example, if you think about the example that I mentioned earlier, training and performance, right? There is a relationship between training and performance. We want to check whether this relationship varies across different fields of education, science and let's say other areas, like science and other areas, right? You can check this relationship. Then you can find in one group this relationship is stronger, which means that training is more effective for that group than the other group, right? So that is called moderation. I'll actually discuss with you two examples with categorical moderators as well as continuous moderators, right? A moderation effect could include positive or negative. Positive means enhancing or increasing the moderator would increase the effect of predictor on the outcome, right? When you get when you increase the level of moderation, in that example I mentioned, we can't see that kind of increase, right? Because we can't say in science or other fields are better than the other, none is higher than the other, right? We can't categorize that. That is they are only nominal. They are only categories. There is no order, right? But when it comes to a variable like, let's say, their income, right? If you get the income as the moderator variable, then we can say when we are getting higher and higher income, what happens to this relationship, right? Then income is also a continuous variable. These two variables are also continuous variables. So we can't find there are two levels or different levels of the moderator variable. Rather, we find increasing or decreasing pattern in the moderator with the increase of moderator variable. What happens to this relationship? Let's say when you are getting higher income, the training has more effect on performance, right? You got a positive moderating effect, which means when people are getting more income, they are getting more, their training program will increase their performance better than low income groups, right? We are not going to actually group. We interpret the result like that. The relationship between training and performance is stronger when people's income is higher, right? Stronger the income, higher the income, the higher the relationship between training and performance. In that way, you can interpret the result. Actually, you have to write hypothesis appropriately, right? Normally, we have these kind of relationships to study many research. So we can actually come up with very interesting results with these kind of this moderating testing, because we can actually identify suitable conditions where some relationships are strong, some relationships are weak, right? You can do the same for studying something in different countries, right? Let's say you are going to find some variable, two variables relationship X and Y in Sri Lanka and in a different country, in developed country, right? You have to take samples from both and you can analyze the relationship between two groups, right? A relationship between X and Y in two groups. If it is different, we can say in one country, this relationship is stronger than the other, right? And also moderating effect could be negative as well, which is then called buffering, where increasing the moderator would decrease the effect of predictor on the outcome, right? When you increase the moderator variable, let's go with the previous example, income, right? If you found a negative relationship, we say training has a positive, let's say we found a positive effect, right? You have to hypothesize positive effect of X on Y. When we increase the training given to employees, their performance will increase. That is your first hypothesis. And the second hypothesis, in the people are getting more income, then this relationship is going to be decreased, right? That means this X and Y variable training is more effective for people who are having less income, right? So you can interpret result, you can tally them with the previous findings of literature, right? Then you can come up with very good findings, right? Most of cases in moderation analysis, you will come up with very interesting analysis. And actually, if you include a moderating variable into many of your models, you can have a research which has lot of contribution, because it can be easily done in any, I think, in many research. In many of our management fields, we can do a lot of things like that, because people have studied, previous researchers have studied a lot of relationship. It could be very interesting to see whether these relationships valid in certain conditions, or these relationships varies across different conditions, right? So that would be really interesting, and that would actually contribute to the literature as well. So you can do good research with the knowledge of moderation. So these are the steps you have to follow, but I'll explain the steps, but I'm sure that you won't get all of these steps clearly until I do an example, right? First of all, the dummy code, when you have a categorical, dummy code categorical variables are manually created and manually create the interaction term, right? When you have if you want to analyze the relationship using a categorical variable, you can calculate the interaction effect. Actually, you have to create another variable in moderation analysis, which is called interaction effect, right? You have to multiply the predictor variable and the moderator variable, and that term should also be included into your model. Both X variable, both independent variable and moderator variable should be there as predictors. In addition to that, these two variables product term must be included. That's the only way to, find the moderation effect. But you have different methods. If you are using structural equation modeling, we are not actually following. We can do this as well. Product concept is there. Indicators product will be considered when you are doing partially square regression analysis. In structural equation modeling, covariance-based structural equation modeling, you use another method, right? You do sometimes this classification and multiplication of the predictor variable and moderator, right? Different tools and techniques are there. But in regression, we normally do this multiplication between x and y, multiplication of x and n, right? X is the predictor variable, m is the moderator variable, right? You have to multiply the term and have calculate the moderator variable, then fit a regression model predicting the outcome variable y from both the predictor variable x and moderator variable n, right? Both effects should be significant. When you start the moderation analysis, you have to include both x and moderator variable, independent variable and moderator variable together into your model. Both both effects should be significant to test the moderator. You need to standardize all the variables to avoid multi-collinearity, because when we are multiplying these two and we are going to include that interaction effect into your model, most of cases we get high multi-collinearity, so we have to standardize the variables first. But when you are using indicators, set of indicators to measure these variables, you don't have to standardize it, because you are getting, as I explained last session, we are calculating the factor scores. When you are doing your analysis based on factor scores, no need to standardize it, right? Because that standardization will happen in the factor analysis, right? And the interaction effect, add the interaction effect to the previous model and check for the significant R-square change as well as significant effect by the new interaction term. You want to after checking these two variables only without including the interaction effect, you have to prove that these two will have some effect on y, significant effect on y. Then you can multiply the two variables and add that interaction effect also into your model. Following the same method I explained last time, you can check the significance R square after adding that variable, after adding the interaction term, right? Then you must have a significant R square change in your model if your moderator is significant. If both are significant, then moderation is occurring, right? Both are significant means your the mediator effect, the interaction effect should also be significant. But two things you have to clarify. If the predictor and moderator are not significant with the interaction term added, then complete moderation has occurred, right? When you got, just suppose that you got significant moderation effect, that means x into y, product term was significant, but x and y, x variable was not significant at that time. And both of their individual effects are not significant, which means this moderation is a full, complete moderation, right? At least x variable is, if x variable's significance is no longer there, then we can say this is a complete moderation, right? If the predictor and moderator are significant with the interaction term added, then moderation has occurred. How this is that is the moderation, right? However, the main effects are also significant. Main effects x and y, x and m variables are significant. At the same time, their interaction term is also significant, which means there is a moderation, right? We can say there is a moderation, right? Otherwise, if only the moderation effect, that means interaction term is significant, it can be categorized as complete moderation, right? If the interaction term is not significant, we can simply say that there is no moderation. That means, just consider the example that I mentioned earlier, related to the relationship between people's training and performance, right? Training and performance. If you check this relationship among two groups based on their education qualification, right? Based on their education background, if you found that there is no significant effect of the interaction term, we can say that there is no difference between training and performance. There is no difference in the relationship between training and performance, because at different levels of people, at different backgrounds of education, right? All the people, if coming from science, management, arts, or any stream, the same relationship can be assumed, right? We can observe the same relationship between training program and performance, right? If this relationship is positive with certain regression coefficient, we can say that is the relationship between training and performance, but there is no difference in this relationship based on the people's education background, right? That is how you have to interpret the result. I would like to discuss some examples with you so you can get very good idea about this, right? Let's do the first example. You can now open this SPSS file, muscle percent males dataset. This is the dataset. This is a very good study, and this is important study, especially for males, right? Because here we are checking with the training average, training fitness hours, right? You can see when you go to the variable view of this SPSS dataset, average weekly fitness hours. It is this variable, right? Fitness hours. The people's muscles percentage, muscle percentage has some effect of fitness hours. When you, that means you want to check whether when you do more and more fitness training, whether you can increase muscle percentage or not, right? And also they want to check this variable, this relationship at different levels of age, different age groups, right? So these are the hypotheses. Look at these two hypotheses. Average weekly fitness hours is positively related with the increased muscle percentage, right? Average weekly fitness hours is the independent variable or is positively related with the increased muscle percentage. If this hypothesis is supported, that means you have to do more and more fitness training to get more muscle percentage, right? So, but there is some other hypothesis, there's another hypothesis as well. The relationship between average weekly fitness hours and muscle percentage is weaker as people get older, right? So this is not a good news then for all of us, because you are not getting higher, stronger relationship between average weekly fitness hours and muscle percentage if you are if you are older. But it is not still proved, right? We are going to check that. Perform the moderation regression analysis using continuous moderate variable age at visit, right? They have considered the age when they visit the clinic or this program, right? So age at visit is another variable, right? Actually, this age they have collected not using groups, right? Age has been considered as a continuous variable here, right? Or age values are given. The exact, maybe they have collected data on exact age of people, right? And you have, this is a very big data set, the 243 observations are there, right? So, then I'm using the same data set to check this as a categorical variable so that you all learn how to do the moderation analysis with the categorical variable as well. Using the same data set, I will explain both. First of all, since you have the categorical, but remember, you are not going to do that in your research, right? If you have continuous moderator variable, no need to categorize it and check it again and do some multiple group comparison kind of thing, because there is no point, because if your data is there as a continuous variable. But sometimes we have categorical variable like industry, country, age group kind of thing. Then we have to do analysis with the categorical variable. But I am using the same data set to do both for your understanding, right? Let's open the data set now. First of all, follow these steps. First of all, you need to check the relationship between moderator variable and predictor variable, moderator variable, and the y variable, that is dependent variable. So our y variable is this muscle percentage. right? You have to understand first these variables, muscle percentage, and average weekly fitness hours is your independent variable or predictor variable. Age at visit is the moderator variable. Go to analyze, regression, linear. First of all, we are going to do the regression analysis with the moderator and the predictor only, right? And as usual, we have to do a plot. Actually, you have to obtain the scatter plot. That is better, right? I'll get the scatter plot before going to the regression analysis. Graph, legacy dialog, scatter plot, right? I'm selecting simple scatter plot. Y-axis, Y variable is muscle percentage. Select that variable, and next axis variable is average weekly fitness hours. Right? We can see some kind of a positive relationship, but we don't know whether this is strong, because from the plot we can say, we can guess it's not going to be very strong relationship, right? However, you can also get the simple scatter diagram between Y variable and the moderator variable, because it is also a continuous variable. So I am including age at visit as the X variable for the scatter diagram. So we can see some relationship. We don't know exactly linear relationship, right? But actually, since the data set is large, we can get very good result in the analysis. Let's move to the analysis now. This is the command. If you can't remember, I'll go from the first step. Analyze, regression, linear. Dependent variable is muscle percentage. Include that, right? Click on the variable and click on the arrow. Dependent variable is muscle percentage. Independent variables are first include the predictor variable, that is average weekly fitness hours, age at visit. Right? What is the result? ASCA is 25%, approximately 26%, right? Adjusted ASCA is 25%. And the overall regression is significant. From this, you can say that. Let's see, how can I close the view? Yes, I think you all can see the outputs. It is better you also do the analysis with me so you can see it very clearly on your screen, right? Include age at visit and average weekly fitness hours as the predictor variables and get the regression result, right? You got p-value which is less than 0.05. If your alpha is 0.05, we can say this regression is significant, and also you can check which X variables are significant. If you go to the coefficients table, you can see average weekly fitness hours is significant, age at visit is also significant, constant term is also significant, right? But actually, for normally we don't remove, even though it is not significant, it is better to go with that, right? Last time I did in some examples, I removed the constant variable when it was not significant. It doesn't matter, you can keep it, right? There is nothing happened with that, including or excluding the constant term, but we can keep the constant term in our model even though it is not significant. But normally other variables, when you have some predictor variables not significant, in your final model you are not going to include that variable, right? Here actually no problem, all the variables, all the parameters are significant, right? So their p-values are very small. So what we have to do then, we have to get the interaction term. Look at the data set again. you can compute. Actually, the interaction term is already calculated here, but actually that interaction effect has been calculated for the centered variables, right? I will show you what happens if you are not centering values, if you are not centered values and do the regression analysis with the moderator, what happens, right? Let's see what happens. First of all, you need to compute the interaction term, right? So your predictor variable is training hours, right? Average weekly training hours. Weekly training hours, this is the variable, and age at visit is the variable, right? You are going to multiply these two and include this as the moderating effect, right? So I'm going to, since there is a term called int1, I'm going to use another term, right? First, go to transform compute variables. Transform compute variables. Right, target variable, I just say you can include interaction, right? And target variable, you can give any name, right? If you like to have moderator, then you can include moderator. Oh, I think moderator is not good because moderator is age. So interaction term is a better term for interaction variables, interaction, or you can simply say age times training, fitness hours, but it is not easy to include. So I put just interaction as the target variable. What I am going to do is multiply average weekly fitness hours and age, right? Include this variable, average weekly fitness hours, and put asterisk to indicate the multiplication and age at visit, right? Numerical expression is training hours, average weekly fitness hours multiplied by age. Average weekly fitness hours is the predictor variable, age is the moderator variable. Multiply these two variables and have another variable called interaction. In this variable, multiplied variable will be included in this target variable column, right? Click OK. Interaction is the term you have calculated, and it is also a scale variable interaction term. Here you got this variable by multiplying a number of hours, fitness hours, and age, right? This is the interaction term. Now I am going to do the analysis again, including the interaction term as well. You can go to the linear regression now very easily, right? Use this icon to go to the last dialog box. Recall recently used dialogs, right? Click on that, get the regression, linear regression tab. Then you can include, you have already included muscle percentage in our last analysis we did. Muscle percentage is our dependent variable. Independent variables, average weekly fitness hours and age. In addition to these two, now you are going to include interaction term, and also in your statistics, it's better to include this R square change after including the interaction term, whether you will get significantly improved R square value. You can check that. Click continue. Click OK. Right, you can see here the R square change. It's better to include this variable later, right? Here you can see overall model is significant. This R square change is including all the variables. No, so go back to the analysis. I forgot one thing, right? To see by including the interaction effect, did you get any increase in the R square value? You have to include this later, right? Remove interaction term now and go to next, right? You have to do the regression analysis in the way of hierarchical regression to see the interaction effect significance. Significant R square change, right? Then include, after clicking on this next button, you can include the interaction effect. Then you can see both models. First model, you got this R square value, right? Second model, you got this much R square change. It is around 6%, right? Approximately 6% increase in the R square ASCA after including the interaction term, and that ASCA change is significant, right? ASCA change is significant. Then you can guess there should be a interaction effect. There should be a moderation, right? And you can go to the last model, including all the three variables: average weekly fitness hours, age at visit, and interaction term, right? Now you can see earlier you got age as a highly significant variable. Now its p-value is 0.04, right? It is not that much high. However, it is also significant. Average weekly fitness hours p-value is also less than alpha, and interaction effect is highly significant. And you can see the coefficient of interaction effect is negative, right? Negative. But we are not assuming positive or negativeness in our hypothesis. We have not, we have written that, right? Let's go to the hypothesis. I think we got that. So, what is the relationship between average weekly fitness hours and muscle percentage is weaker as people get older. So, are you going to check a positive or negative relationship? Positive or negative moderation we are checking here. The relationship between average weekly fitness hours and muscle percentage is weaker as people get older. Is that a positive relation, positive moderation or negative relationship? Negative moderation you are hypothesizing here. Age, when you increase people's age, you are getting weak, you are expecting a weaker relationship between their fitness hours and muscle percentage, right? So positive or negative?
Negative.
Negative relationship, very good. So it is a negative, we assume a negative relationship, and also we got the same result. Right? So otherwise you can't say, just by looking at the regression coefficient, you are not going to say it's a negative relationship, right? You have to hypothesize that based on previous research, right? People who have done research on this area, maybe they have come up with the idea that when people are getting older and older, normally normal fitness hours will not work when it comes to muscle increase, muscle percentage. So that kind of background literature must be there, right? Based on that, you can have a negative moderation effects hypothesis. Then you got a negative relationship. Then you can hypothesize. You can say that you can confirm that hypothesis with your data. You can say when people getting older, the relationship between here you can see the positive relationship between average weekly fitness hours and muscle percentage, right? So it's a positive relationship, but it is not bad. It is weaker when people are getting older, right? So, but still we are not sure whether our result is correct or not. What do you think? Did we center values? Did we check any multiple linearity? Because our interaction term we obtain by multiplying x variable and moderator variable. It is very important to check the multicollinearity at this stage. If you are not done that, it is wrong, right? And the other thing is, I forgot to mention another thing. If you have hypothesized a positive relationship or negative relationship, this p-value must be divided by 2, right? It doesn't matter. This value is also less than 0.05. Definitely, half of that will be less than 0.05. No problem with that. However, if you have if your hypothesis is one tail, right tail or left tail, your p-value must be divided by 2, right? So I'll now get the result, the same result with the collinearity diagnostics. So do the analysis again. I'm going to, you can now include this interaction term also at the same model, because you just to check the check whether the interaction term is adding interaction term will increase significantly our ASCA value. I included that variable separately. Then you can include all the 3 variables together and go to statistics and click on collinearity diagnostics. Continue. Okay. Look at this. Now ASCA change is not important, right? We already know that. And look at the VIF values. Look at the VIF values. They are very huge, right? Definitely there is a serious multicollinearity issue in your module. So module is not good. Even though you have fitted the module, it is not actually, it is not good. So there is a multicollinearity problem. So to eliminate that, we have to center the variables, right? But for our convenience, I have given you the centered variables as well. You know how to get the, say, how to center the variables. We did some examples last time, right? Center the variables. When you want to get the centered age, for example, calculate the average age and subtract the average age from each of these age values and have the centered value here, right? So centered age is that. Same way you can calculate the average weekly fitness hours centered. If you go back to the data set, you can see actually these centered variables were there. When I'm getting this data set, all these centered variables were also there. So I didn't calculate this, but you know how to calculate it, right? Age at visit centered. Within brackets, it says it is centered. Average weekly fitness hours centered. Interaction term, int1 means that interaction term, right? This interaction term we just got by multiplying age and average weekly fitness hours, which gave us a model with multicollinearity problem. So we are not going to use this interaction term any longer, right? So we go with this interaction term. We have some int1, that interaction means age at visit, average week multiplied by average weekly fitness hours, both centered. That means this interaction term int1 means age at visit centered value multiplied by average weekly fitness hours centered value, right? Multiplication of both centered values, right? That is the interaction term. So I'm going to do the analysis again. But here I'm not going to get the ASCA change, which is not important. We already know that to increase the ASCA value. Also, you can try that with the centered value. So you can include the interaction term next, right? Because we don't know whether we got the significant result because of the with this multicollinearity issue, whether it's there or not, right? So I'm going to include the interaction term variable after including predictor variable and moderator variable, right? Let's go to the, let's get the ASCA change and also collinear diagnostics. This is the result. There also there is no difference in the ASCA value, right? So we get significant result. This is the final module, including all the three variables. And here you can see the VIF values. VIF values are very small, and these are the standardized coefficient. I think in the earlier model we got very higher values for the standardized coefficient, which is also which is happening because of the multicollinearity problem. But normally we get standardized coefficients between -1 and +1, right? We have to get values between -1 and +1. If you get larger values for say standardized coefficients as we got earlier, that is a problem in the model because of multicollinearity, right? So here our model is now okay, now very good, because it has very low VIF values, right? VIF values are very low. There is no multicollinear problem, and the final model's ASCA is around 31%, 32%, right? Adjusted ASCA is 31%. So, however, it is not that much predictive modeling. Predictive ability of this model is not very high, because we can explain actually 31% or 32% of variability in muscle percentage. That means average weekly fitness hours is not the only factor affecting muscle percentage. You all know about that, right? Your protein intake and so many other factors may affect muscle percentage, right? But here we are checking, our target is not to check the percentage explained, check what percentage is explained by this factor, but we want to know whether there is significant effect of training hours on muscle percentage. we got that result. It explained around 31% of muscle percentage. And VIF values are low. We can say this model is good, right? Interaction effect is significant. So, and also average weekly fitness hours positively related to muscle percentage, right? That means when you are increasing average weekly fitness hours, you can expect good result in the muscle percentage. But the problem is, when you are getting older and older, this effect is going to be low, right? This effect is low when you are getting older, right? So, since we have used age as a continuous variable, we cannot say which we cannot see the difference, right? But we can just say when people are getting older, the average weekly fitness hours effect on muscle percentage is going to decrease, right? But now I'm going to do the same analysis with a categorical variable.
Dr. Chaturani,
Yes, sir.
before that, can you clarify that whether there is a fully moderating effect or
Sorry, sir, I didn't get your point.
whether there is a fully moderating effect?
All right, it is not fully, sir, because in the last model, yes, thank you for your question. And the last model, including all the three variables together, you got significant result of all significant p-values for all the variables. Still, after including the interaction effect also, average weekly fitness hours as a relationship, age is also significant, and also interaction effect. If all the variables are significant together with the interaction effect, we say it's a moderation. We can't say it is complete moderation. If it is complete moderation, only the interaction term will be significant, right? Interaction term may be, but especially this predictor variable should not be significant in the final model if it is a complete moderation, right? But here all the variables are significant, including the interaction. Therefore, this is just a moderation, and also it's a negative moderation. It's a negative moderation, right?
Right, thank you.
Okay. So now I'm going to use the same data set for testing this as a categorical moderator. Just suppose that you don't have people's exact age, right? In most of our studies, we collect data at age we collect data for age in categorical format, right? But here, actually, what I did was since I have the original age data, I calculated, I divided this into 3 groups, right? Equal 3 groups, so that every group get similar percentage, right? Actually, when you are testing categorical moderator, it is also important to have not exactly same, but approximately equal percentage of observations for each category. Suppose that you are checking some relationship between 2 variables in 2 industries. You have electronic industry and food industry, right? You have more access to food companies. So you got 100 data from food companies, and they say you have only 20 companies from electronic industry. Your analysis may not be that much fair, right? Because you have only 20 electronic companies and 100 food companies. So mostly your data set is food companies, right? So it is important, if you are checking a moderator, the approximately equal amount of observations must be there for each category, right? Here actually you have not only one level of age, right? I have categorized this into 3 categories, right? Look at the age category variable. You can go to the variable view and check. Go to the values, click on this, right? I have given 1 for youngest group, 2 for the middle age group, and 3 for the oldest group, right? There are 3 groups, right? So, before checking the moderator, that is also one of the methods you can apply for checking moderation, right? You can check the same relationship between X variable and Y variable, not including the mediator variable, right? But divide the whole data set into groups based on the moderator variable and check whether there is a difference between the regression coefficients, just to observe, right? You can do that for your observation, right? So to do that, actually you have to split the worksheet according to the categorical variable that's your interest, right? Our categorical variable is age category. So you can divide the data set into few you can do the analysis by splitting the worksheet into categories, right? So to do that, actually it's better to save the data set using a different name, right? Save the data set using a different name because the that command will sort the whole data set, right? If you want to see the original data set again, you have to save this as a separate file. So I'm going to save this file again. File save as, right? You can also save your file using a different name. Right? Save as, give a different name. Muscle percentage males 2, right? You can give a name like this, right? New data set. I'm going new, right? Muscle percentage males new. Save. Now I'm going to do the regression analysis between muscle percentage and average weekly fitness hours just by grouping the data set, right? Here, since you don't have any issue with the multicollinearity, maybe you can include these two variables, original variables, right? So do the analysis, go to regression, linear regression, first of all, you have to split the worksheet, right? This is how you have to split the worksheet. Go to data, data menu, select split file, split file. Split file, right? It will not create two separate worksheets. That also can be done, but we want to compare the regression results between age groups. That is what you want to do, right? So I'm selecting this one, compare groups. Compare groups. Then you have to specify the categorical variable on which the groups are based on, right? Groups are based on age category. So I'm going to select age category as my categorical variable. Now, any regression or any kind of analysis you do, it will divide the whole data set into groups based on age category and present the results separately. Simply, this command will give you several outputs based on the categories available in your grouping variable, right? So compare, then age groups, include age category as a variable, right? And this will automatically happen. Sort the file by grouping the grouping variable, right? If your file is already sorted, you can select that. Otherwise, it will be sorted. That's why I save this file using a different name, right? Then click OK. Right? So I didn't do any analysis. I just split the worksheet. So I'm going to do the analysis now. Linear regression. Dependent variable is muscle percentage. I'm going to take this interaction term away and go to previous one. Now you can include average weekly fitness hours. Muscle percentage is your Y variable. Independent variable is average weekly fitness hours. Right? We don't need to get this square change and code it in diagnostics. There is no one, we have included only one variable, so no need to check the multicollinearity. Here, as I mentioned before, there are 3 regressions for the youngest group, middle age group, and oldest group, right? And here you can see all the regressions are significant except oldest group. It's a very interesting result, right? You can very easily see the difference here. Regression coefficient, if you look at the regression coefficients also, you can see average weekly fitness hours beta coefficient is, if you look at the standardized coefficient, it is 0.594 in the youngest group. Middle age group, the coefficient is 0.492. The relationship between average weekly fitness hours and the muscle percentage, right? And what about the oldest group? Oldest group is 0.068. 0.068 is the standardized coefficient, which is not significant. If you just consider the oldest group, there is no relationship, there is no significant relationship between average weekly fitness hours and the muscle percentage, right? So this is also another way of checking the moderation. With this result only, you can say there is a significant moderation effect of age on the relationship between average weekly fitness hours and the muscle percentage, right? When people are getting older, their relationship, there is no chance to get muscle percentage, increased muscle percentage by doing fitness hours. If you want to know more about these three groups age categories, I would like to get the show you the descriptive statistics. Go to analyze descriptive statistics, descriptives of three age groups, right? I would like to get the mean values, right? You can get mean and standard deviation. Minimum maximum is not important, right? Mean and standard deviation of this age, right? We want to know the average age of each group, right? You can see here. So, but here again the file is splitted, so you have to remove that, right? Go to split file command and select this button, right? Select this option. Analyze all cases, do not create groups, right? Otherwise, all of your analysis will be grouped, right? Will be presented using these groups. So I'm going to get the whole result. Then click OK. No, now get the descriptives for age. Here you can see. Yeah. No, this here you have to get the average groups. Average of all the groups separately. So it is better to split the file, right? We want to check the mean of three groups now. So that is important, right? Age appreciate. So you got the result for age groups. Yes, this is the right one, right? Average age of youngest group is 23.79, middle age group 29.6, and oldest group 42. There's no much difference, right? No much difference. We have not taken people who are very old, so it's a not good sign for us because most of people are about 42 or close to 42. So in this stage, there will be no significant result of getting more and more average weekly fitness hours. It will not increase your muscle percentage, right? Because actually people's body will build up to certain age. Otherwise, after that age, muscles will not build up. So that is the final conclusion. That is how you can. That is one way of checking the moderation, but that is not the right way, because sometimes here you got the result, different significance levels in different groups. But I will explain the normal procedure, formal procedure of checking categorical moderator, right? Categorical moderator. Here you have three age groups. So you cannot simply multiply this age group by the X variable, right? You have to make a dummy variables, two dummy variables for representing this, because you have three groups. You have three groups: youngest, middle age, and oldest group, right? Three groups. So to create the dummy variables, it is not easy with SPSS, right? SPSS, I think a very latest version should be there to create the dummy variables for these ones. So easiest way of doing that is using Excel, right? So go to your age group variable, right? Age category, copy this variable to an Excel file. Copy the age category variable to an Excel file. This is age category. So I'm going to paste it here. Age group 1 means youngest group, right? Youngest. And middle age is 2. Oldest group is 3, right? So I'm going to create 2 dummy variables. To represent 3 categories, you need to have 2 dummy variables, right? I will expand the size of this. This is the age category. And I'm going to name these dummy variables as D1 and D2. Right? How to identify these dummy variables? Actually, you have, this is important. It is important to have zeros and ones only to represent the categorical variable in order to find out which age group with more, which group has moderation, which group is significantly different from the other in the regression relationships, right? So I'm going to use zeros for age group 1, right? Both variables are 0, right? Both variables are 0. So just drag this up to the last one, right? That means first youngest group. For the youngest group, both dummy variables will be 0. Since you are doing mix manually, you have to be very careful. Don't go to the other group, right? All the youngest group people, both dummy variables are 0, right? Right? Then to the middle age group, I'm going to put 0 for the first dummy variable and 1 for the second variable, right? Second dummy variable. So this is the coding for age group 2, right? 0 and 1. All the middle age group, 0 and 1. All the third level group, third level means oldest group, right? First variable is 1, second variable is 0. Right? Actually, here you have identified, this is actually a way of identifying variables. Age category 1 means the youngest group means both variables, both dummy variables, 0. That is going to be actually the reference model in your analysis, reference model, right? So both variables will be 0. When you get second category, you have first variable as 1, right? So if your dummy variable 2 is significant, that means there is a difference between youngest group and middle age group, right? Because only second dummy variable is 1 for the second group. So for the second group, that is middle age group. For the third age group, you have 1 for the dummy variable 1, right? Dummy variable 1. If dummy variable 1 is significant, interaction effect related to dummy variable 1 is significant, we can say third age group is different, right? So I'm going to copy these 2 variables to the data set, right? So I think you have to select this data only. You can give the names in your worksheet, right? Copy these 2 columns, 2 dummy variable columns. Copy. Click on here and paste. This is dummy variable 1, this is dummy variable 2. You have to give these names in the variable V. So I'm going to give D1 and label also D1. Sorry, D1. And we don't need decimals because they are zeros and ones. So remove the decimals. Second variable is D2. Right? So you have two dummy variables now. If you have only two categories, no need to do this, right? You can simply put 0 and 1. One age category can be classified as 0. The other one can be grouped as 1, right? You cannot go with 1, 2, 3. You have to give 0 and 1. 0 and 1 if you have only two categories. But here you have three categories. So to compare their interaction effects, you must create the dummy variables. That's why I created two dummy variables since you have three categories, right? So three categories are now identified like this. Both the dummy variable 1 and dummy variable 2 are 0 for the first category. Only dummy variable 2 is 1 for the second category, that is middle age group. And for the third category, only the first dummy variable is 1, right? Then you can include these two as the moderators, but you have to get the interaction effect as well. Interaction effect is normally calculated by multiplying your moderator variable with X variable or predictor variable. Your predictor variable is, yeah, you can get the centered age, right? So now I'm going to get the interaction effects. We're going to calculate two new variables. Go to transform compute variables. In the transform menu, you'll find compute variables command. Yeah, Aminda has sent me a question. What happens if you have three categories? You have to calculate actually three dummy variables. It's not easy to do with using manual methods, right? Actually, there is a package called Minitab. You can easily create all the dummy variables using Minitab very quickly. For any number of categories, you can create the dummy variables automatically. You can create the dummy variables. Here, if you have 4 categories, actually you have to use 3 dummy variables, right? All the 3 variables 0, all the 1 variable 0, other one is 0. So it's not easy, right? To do manually, right? Now I'm going to calculate interaction effects. Now I'm going to get the interaction effect of B1, right? Int and right, type it here. Target variable is int underscore D1. That means I'm going to multiply D1 variable with the muscle percentage. Average weekly fitness hours, right? So multiply average weekly fitness hours by D1. This is the interaction between one age group and average weekly fitness hours, right? Now you can see here interaction term is given, right, in this column, right? Do the same for the D2 variable as well, compute variable. Now I'm going to give a different name, interaction 2. Int underscore D2 is my variable name, int D2. Now multiply this average weekly fitness hours by D2 variable, right? Select the variable D2. Double click on the variable, then it will come to your expression. So click OK. You can find here the interaction term, right? Interaction terms is calculated using the value of weekly fitness hours multiplied by D1, that is first interaction term, second interaction term, right? Now we can include all the variables together, but remember that you don't have variable called age now. You have collected data only in age groups. You have only age category, right? Forget about this original age variable, right? Now go to analysis regression, right? And regression analysis, linear regression. First, we are going to include average weekly fitness hours and age category, right? Or no, actually, here we have 2 dummy variables. We are going to include the 2 dummy variables. Same age category variable is now represented in terms of D2 and D1 and D2, right? So no need to include age category variable. You have to include D1 and D2, right? Because you have interactions with these two Include all the 3 variables. Click OK. No, actually, I have splitted the worksheet, right? Now you are not going to split the worksheet. Splitting worksheet is another way of checking the moderation. Actually, that is a very good way to visualize the moderation, right? But now I'm going to combine the worksheet again. So click on this option, analyze all cases, do not create groups, right? Do not create groups. Go to linear regression analysis again. Include average weekly fitness hours. This is your predictor variable. No, actually, it is better to include the centered value, right? I'm not sure how did we get the age, right? I think we calculated these 2 variables using the age value, right? Sorry, only age, right? Delete these 2 variables now because we are planning to get the centered value. Centered value, getting centered value is better in this kind of analysis, right? Moderation analysis. So calculate again. Go to compute variables, transform compute variables. I'm going to first get interaction D1. Interaction D1 is centered age. Get the centered age. Age at visit centered. Sorry, not age. Sorry. Average weekly fitness hours centered. Average weekly fitness hours centered. Right. Include that variable. Centered average weekly fitness hours multiplied by D1. Right. Centered average weekly fitness hours multiplied by D1 is interaction term D1. Click OK. Right. Then compute the variable again. Now new variable is interaction D2, int underscore D2, and we are going to multiply average weekly fitness hours, centered average weekly fitness hours by D2 variable. Now these are the interaction terms, right? Now go to regression analysis. Regression analysis, I'm going to include first average weekly fitness hours centered variable. Centered variable and moderator variables D1 and D2. Right? Don't include the interaction terms in this stage, right? Now you can get the result. Here, actually, you got only one age group significant in this result. Overall regression is significant. Overall regression is significant. And when you go to the coefficient table, you can see average weekly fitness hours is significant. And D1 is significant. D2 is not significant. That means it's a one indication of the moderation. Actually, D1 and D2 both are age category, age variables, right? D2 variable is not significant. That means in that age is, D3 is representing the oldest group. That age is not a significant variable in this age, right? So, but this is not enough for checking the moderation. You have to include the interaction effects, right? Don't remove any of these variables. Go to the linear regression again. Actually, to check the R-square change, you could have included these 2 variables after including this variable, right? But here in this example, we already know that this age has significant R-square increase. So I'm going to include now interaction terms, interaction D1 and interaction D2. Now you can see clearly the difference, right? Go to the analysis result. Average weekly fitness hours, p-value is small. That means it is significant, right? That means there is a significant relationship between average weekly fitness hours on the muscle percentage, right? And D1 is significant, D2 is not significant. That means at least one D variable is significant, means age is a significant variable, right? Age has some effect on muscle percentage. Their individual effect is there, right? And also interaction effect is significant. Means interaction B1 is only significant. Interaction B2 is not significant, right? That means at least if one of these two interaction terms is significant, we can say there is a significant moderation of age. There is a significant moderation of age. And also you can see the moderation effects, interaction B2, moderation effects, coefficient is negative. That means there is a negative moderation of age. When people get older, the relationship between average weekly fitness hours and muscle percentage is going to decrease, right? So the same result is there. However, you are getting more variables in this analysis when you are having categorical moderator, right? But if you have only two categories, the analysis would not be this much complicated. Here, I got a complicated situation having three categories, right? Three categories, because otherwise I won't be able to explain how to deal with three categories when you have moderator. Then you will learn only checking moderators of two categories, right? But this method you can apply for categorical variables at with any number of categories, with any number of levels, right? Actually, what we are checking here with the interaction, I mean, D1 and D2, compared to the youngest group, what is the significance of the relationship between X and Y variable in age group 1? Age group 1 is middle age group, right? Middle age group. D2 means oldest group, right? Oldest group, you have no significant moderation, right? Actually, the result is, you are not saying that it is separately for, the result is not interpreted separately. At least one interaction term is significant, because if B1 and B2, both of these variables represent age, right? So at least if one of these two interaction effects is significant, you simply say that age is a significant moderator. Age is a significant moderator for the relationship between average weekly fitness hours and muscle percentage. Average weekly fitness hours and muscle percentage. And one important observation is here, you got very low R-square value compared to our previous analysis. We got very low R-square value, as I remember, in the continuous moderator analysis. We got more R-square value, right? That is the, from this R-square difference, you can understand what is the disadvantage of using categorical variables, right? Disadvantage of using categorical variables. If you are using age as it is, it means you are not losing any information. Here you are using some of the information. What is that? The people's exact age. You are missing that. You have categorized them into groups: young age, middle age, and old age. But still we are missing some information. We have only three categories, but when you are using this variable as it is with the exact age, right, your result is better, right? Always, therefore, try to get your moderator variable if it is continuous, right? If it is an industry or some kind of categorization, grouping, no point of getting a continuous variable, right? I have examples with multi-item scales. So you can check those relationships, categorical as well as continuous variables. So I think you understood the whole analysis, right? If you have any questions, please send me a question through the chat, or you can ask now before moving to the second example, because all these three examples have different characteristics, different data characteristics. Any questions?
Dr. Chaturani, can
Yes.
if we have two categorical variables, I mean,
Yeah.
two groups,
Yeah.
so no need to calculate dummy variables, no?
No. That's simply you have to do, what you have to do is identify the first category as 0, then second category as 1, right? In your data sheet, suppose that you had only two age groups, go to age category here, right? Here age category, we have put 1 for youngest group, 2 for middle age and oldest. Just suppose that you have only 2 categories and name 0 as the first category, right? Youngest and older, right? If you have only 2 categories, give one category, name one category as 0, the other one as 1. Then you can use that variable as it is for your analysis and multiply the moderator variable and the X variable and have the interaction effect directly. But if you have 1, 2, 3 kind of values, we cannot do that, right? 0 and 1 is better, right? Otherwise, you have to create, if you have more categories, you have to create dummy variables. Okay. Okay, now we can go to another example. Still, you can ask any question if you have. You can send me a question or disturb me at any time. Any point I can answer your questions, right? Actually, I have given, after that, I have given only examples, right? Because you all know about the theory, what is happening in moderation, what is negative moderation, what is positive moderation, everything is explained. Would you like to have about 10 minutes break before moving to this example, these 2 examples? Is that okay, sir?
Yes.
Yeah.
Understanding.
Let's have 10 minutes break and come back. Actually, I want to again go to the interpretation part of previous analysis because actually there is small issue in our categorization. It doesn't actually, it is not an issue, but when you are going to interpretations, it will make some difficulty there, right? Because we considered first category as both zeros, that is normal way. But actually I put D2 variable 1 for the middle category. That means middle age group is represented by D2 because only D2 variable is D2 variable equals to 1 when you consider the middle age category, right? If you look at the output, D2 variable is not significant, which means in the middle age category, there is no difference compared to the reference group. What is our second reference group? Reference group is the category which has both zeros, right? That means reference compared to the youngest group, there is no difference in the D2 variable actually represent not the last category, but the middle age group, right? So here in our analysis, D2 is for the middle age group, right? Whatever the group coding you use, you better mention, note down that somewhere, right? D2 variable 1 means D2 equals 1 means middle age group, right? Middle age. For the category 2 only we use D2 variable 1, right? If I use the other way, if I use D1 equals 1 for that category, that would be better, right? For our comparison. And D1 variable equals to 1 for the oldest group. That means D1 variable represents oldest group. Right? This you have to remember this coding when you are going to interpretations, right? In the interpretation, you can see the output. D1 group, only D1 variable is significant. That means age group oldest group has some difference. Oldest group age has a significant impact, and compared to the youngest group, there is no difference in the middle group, right? Middle age group is D2, middle age group, and also interaction term of D1 is only significant. That means only the oldest group is significant, right? However, the overall interpretation is age is a moderating variable, age is a significant moderator, and that difference is seen in the first group, D1. D1 means oldest group, right? Other 2 groups are not different. That is also some extension, further interpretation of our result. Result is okay, but you have to go to your interpretation with this grouping, right? Because we got oldest group represented by D1 and youngest middle age group represented by D2. If I interchange the grouping, but dummy variable values, then it will be better, right? However, whatever the coding you used, you have to remember that. right? So interaction term associated with D1 was the only significant one. That means D1 group is significantly different from the young group, right? But both young group and middle age group are not different. So now I think we can go to the new example. This is example 2. I think you have read the question and the hypothesis. We have used this data set, part of this data set before for discussing the moderation effect. Also, I use same data set, but I have saved this file as separate file called lean moderator, right? In your data folder, you can find the file called lean moderator, right? Open lean moderator file that includes the categorical variable firm size, medium and large firms, right? Medium and large firms test whether the firm size significantly moderate the relationship between lean practices on performance, operational performance, right? You are checking the relationship between lean manufacturing practices and operational performance. Lean manufacturing and operational performance, right? So, this relationship, you want to check whether this relationship varies across different firm sizes, right? You have only two categories, medium and large, right? It is now easier, medium and large. First hypothesis, H1 is lean manufacturing has a positive impact on operational performance, right? Our hypothesis is positive relationship between lean manufacturing and operational performance. When organizations do a lot of lean practices, and it will lead to high operational performance in that company. And the second hypothesis is firm size moderates the relationship between lean manufacturing and operational performance. That means this relationship, whether this relationship vary across different firm sizes. Are you hypothesizing a positive or negative moderation here? Positive, if it is a positive relationship, which means here we have to assume that we have to hypothesize that when firm size get larger, then this relationship is high. If it is a negative relationship, we need to assume that when the firm size get lower, I mean middle group should have a larger effect than large firm sizes. But here we are not having that kind of a hypothesis. Maybe, probably we don't have any literature or any justification to hypothesize any positive or negative moderation. In that kind of situation, it is better to have hypothesis like this, right? This is actually a two-way hypothesis. Firm size moderate the relationship between lean manufacturing and operational performance, but we don't know positive or negative moderation. If there is some difference between medium size and large organizations, in terms of the relationship between lean manufacturing and operational performance, we can simply say that firm size moderates the relationship between lean manufacturing and operational performance. But we are not going to say which companies have, which size of companies have more effect of lean, right? That can be recommended for a further research, right? If you got a negative effect or positive effect, positive quotient, you are not going to say anything, but you can recommend this since we observe an indication of a negative relationship or positive relationship, that effect can be tested, right? You have to find some justifications to prove that, right? Before going to that, I would like to open the data set and start the analysis, right? Later on, we can go to the interpretation part. I actually always try to go to the interpretation part more, because even though we are getting very important, very nice statistical outputs, when people don't know how to interpret the result properly, your findings will be wasted, right? That's why I always go to the interpretation part. So let's open lean moderator file. Actually, here I have already calculated all the operational performance and lean manufacturing and interaction effect, all the variables. But some of you would like to do this again with the factor analysis and obtain these factor scores again. Would you like to get that part as well? It will revise your memory about the factor analysis and how to get these scores and all. What do you think? I think we have enough time to do that.
then that's fine.
Yes, yes. So it's better we delete all these variables, right? Because it will revise your memory on validation part as well, right? Model validation and calculated factor scores and all. So I'm going to delete all these three variables, OP, LM, and interaction, right? I will show you how to get these variables. So remove these variables, remove the calculated variables. Here you have only two variables to do the factor analysis, two sets of variables, lean manufacturing and operational performance. Size of the firm is not included into your factor analysis because it's just a categorical variable and you have two categories only, right? 0 represents large and 1 represents medium, right? So I think it is also better to always use the larger value for the large category. That was the mistake in for the previous analysis also. So I would like to interchange this category notations, coding, right? So I'm going to code this again, having 0 for middle size group and 1 for large, right? Sorry about that mistake. So it's okay, but you can compare. You can compare if you have zeros and ones, but it is not easy to remember that larger one is the small, having the smaller value, right? So I'm going to code this again. Go to this recode into same variable, or you can simply use another variable, another column, recode into different variables. Go to transform menu, select recode into different variables. Recode into different variable. I'm going to have a size variable, recode that variable. Size underscore new. This is my new variable, size new. I'm simply trying to change the values zeros and ones of assigned to large and medium group. I would like to have 1 for the large group and 0 for the middle size group, right? So old and new values you can specify here. Now earlier value 0 now should be changed to 1. Earlier value 1 will be now 0. Right? Then click the old, I will give the old value and give the new value and add, right? Click on add. So likewise, you can give both categories here and click on continue and change the variable, right? Previous variable is size. Now new variable is size new. Click on change. Then it will come to here. Size variable will be converted into size new variable having different coding. I just change the coding, right? That's all. For our interpretation easiness. Now look at the data sheet. Right, I will remove the decimal points. Whenever you have categorical variables, better to have the variable without the decimals. Here now you can see earlier 1 values are now zeros, earlier 0 values are now 1, right? So I'm going to remove the previous variable. It is not important now. And now new 0 values is medium size. So you can give the label like label here. Size new, sorry, not label, not label, values, right? Values. 0 means, sorry, 0 means medium size. Medium, then click on add. 1 means large. Now I change the coding. Right? 0 means medium organizations. 1 means large organizations. You can also check how many large and medium organizations are there. Go to frequencies, analyze descriptive statistics frequencies. I'm just getting the frequencies of both sizes of organizations. Here you can see medium organizations. There are 87 medium sized organizations, 85 large organizations, approximately equal grouping, which is important for the moderation analysis. So before going to do that, you have to have individual variables for the operational performance and lean manufacturing. But we have sets of variables. Simply you can use these variables as it is if you are using a structural model. but you have to do some, you have to get some factor scores if you are using SPSS or regression analysis to do this and this moderation, right? So go to factor analysis. This is what we did last time. If you can remember, you can do that without my help, right? Go to analyze and dimension reduction and factor. Include all the variables, all the continuous variables, right? Don't include size. All the variables, LM and OP variables. And go to extraction, rotation. We are going to select Promax rotation. Click on continue. And extraction method is definitely principal component, right? I'm not going to store the score set, right? Before going to do that, you need to evaluate the reliability, validity of the model constructs, reliability and validity, right? So now you can click OK. Look at the pattern matrix, but here actually I didn't hide the coefficients having lower weights, lower loading, so I can do that. Go to factor analysis again and options, go to options and select this option, suppress small coefficients. Then you can easily see the differentiation between factor loadings, right? So I'm going to click on this suppress small coefficient and give 0.3. That means all the factor loadings below 0.3 will not be displayed. It doesn't mean that the values are not there. We just don't see them, right? Click on continue. Now you can see the pattern matrix. You can easily see the patterns. And here, our interest is having all the LM variables together and all the OP variables together. But we don't see that kind of nice pattern here. So we need to do something. We did similar, same data set with some other variables last time. Here you can see OP, when you consider LM variables, all starting from LM2 to LM6, all the variables are having high loadings into the second component, but one is LM4 as the highest weighting in the third component, which is right, which is not going to be our interest is to have only two factors, LM and OP, but here we are getting three factors, right? Because of our because this we are doing exploratory factor analysis, it will generate n number of factors, right? Based on the data characteristics, but we want to get only two factors, right? So look at the variables belong to LM, which are loaded into the other factors, right? LM3 is okay. LM4 has higher loading here, but it is 0.49. LM5, LM6 don't have any issue. But look for any LM variable loaded into another factor having larger loading, right? Here you can see LM3. LM3 is LM3 doesn't have any issue. LM3 has another loading to the component 1, which is also not that much high, 0.3 something. This is 0.9. There is big gap, so there won't be any discriminant validity issue here. But LM2 has a higher loading to component 3. That higher loading is 0.6, and LM1 has the highest loading to component 1, and it is also 0.6, right? That means both LM1 and LM2 are loaded into different factors, which we don't expect, but their loadings are 0.6, right? It doesn't matter. We can select to remove one variable, but we have to look at the OP variables as well. Normally, we remove the variable which has highest loading with another factor, right? Highest loading with another factor. If you look at OP variables, all the OP variable except OP1 and OP6 are loaded into the same factor 1, right? Which is very good, because many of LM variables are loaded to component 2, many of OP variables are loaded into component 1, which is good, right? And if you look at OP1, it has a higher loading to the second component and its weight is 0.653. OP6 is loaded to the third factor, but its loading is really high. So which variable you are going to remove first? Several variables you found loaded into other factors, LM1, LM2, OP1, OP6. But the highest loading with another factor is the loading with OP6. It is loaded to third factor, which is not of our interest, and it has the largest loading. Therefore, we are going to remove OP6 first. Don't remove any of other variables in the first step, right? Every step you remove only one variable. Remove OP6 first. So go to factor analysis again. Remove OP6. Still you are getting three factors. However, now OP variables, OP2 has some issue. OP2 is loaded to this factor and this factor, both 1 and 3, but they are very low, right? Their loadings are low. So don't look at that value now. OP1 is loaded to the second factor and its weight is 681. And also LM2, all the LM2 variables are loaded in the second component, but LM2 is loaded to the third factor having very large loading. So what is the second variable you are going to remove? LM1 also has a problem, but its weight is lower than this. So what is the second variable you are going to remove? There are three options, LM1, OP2 and LM2, but highest loading to another factor is there with LM2. Therefore, I am going to remove LM2. Now we got only two factors, which is very good, and also cumulative percentage of variation explained by the two factors is around 62%, which is also really good. And now almost all the variables are loaded according to our wish, right? But still LM1 is loaded to the first factor. Its weight is 617, and OP1 is loaded to the second component, which is normally representing LM. So this could be a problem, right? This is the largest weight loaded into a different factor, right? All other problems are now almost resolved, right? But still LM4 is an issue. Even though it's the highest weighting with the second factor, the difference between this 0.3 and 0.4 is not that much high, right? Probably we have to remove this later, but we are not going to remove that in this stage because OP1 has the most serious issue here. So in this stage, I am going to remove OP1. Remove OP1. Okay, still the two factors are there, and also you can see factor cumulative percentage of variability is also equally high. If you go back to pattern matrix now, now all the LM variables, LM3, LM4 still has some issue. LM3, LM5, LM6 all are loaded into the same factor. OP1, sorry, OP2, OP3, OP4, OP5 all loaded into this factor, right? But still LM1 is loaded to a different factor, therefore its weight also high. So I'm going to remove LM1 now. Maybe you don't lose this much variables if you are using a structural model, because you can easily assign the correct indicators to the relevant factors. Still you actually remove sometimes variables based on some other observations. But here I think it is very likely to remove more variables, right, in this exploratory factor analysis. That's another shortcoming in this regression based factor analysis based regression with SPSS, right? So now you can see LM3 has no issue. LM3 is loaded to the second factor. This is very low compared to LM3. So no need to worry about that. But LM4 is loaded to both factors and it has higher loading to the first factor, which is also not good. Other variables are okay. And OP2, OP variables all are okay. 2, 3, 4, 5, right? But we would like to have loadings at least larger than 0.6. But still we are having some little, low value for OP2, doesn't matter. No need to remove this, but you can check in the next stage, right? I'm going to now remove what? LM4. LM4 because LM4 has a higher loading to another factor. If you go to the pattern matrix, you can see LM3, LM5 and 6 all are loaded into the second factor, and OP2 now its weight is also a little bit improved. Its loading is now 0.508. 508. All other loadings are larger than 0.7, which is really good. And these loadings are also high. This is 0.66, that is okay, right? 0.5 value is 0.4 is also okay, but if there is a risk of having this unique validity, if this variable has loading, larger loading over here as well, right? Actually, you can check the convergent validity and discriminant validity from this result. You have to calculate the average variance extracted value, AV value, and discriminant validity is already justified here because you don't have any, all the weights lower than 0.3 will not be displayed, right? So it means that all the loadings which are not here are lower than 0.3. If these values are 0.3, these loadings, our obtained loadings are larger than 0.3, right? So there can be some problem in OP2. If you look at the exact value, you can go to the command options and suppress. You can remove this and look at the result again. OP2, the largest loading into the first component is 0.508, whereas its loading to the second component is 278. It has some difference, right? Some difference, but actually, it is better if you get more than 0.3 difference between these two loadings, right? It is not exactly 0.3 difference. However, since we don't have much variables, we can stop here. Otherwise, you can try removing OP2 as well. But since these 4 variables is good to keep, it is better to keep 4 variables, and there is a significant level of difference between these two. I'm not going to remove OP2 variable, right? It is better to have as much variables as much as possible. And LM variable also, we have only 3 indicators. These indicators don't have any issue, right? To see the result really clearly, I suppress the values. Okay. So now, according to this pattern matrix, component 2 will explain lean manufacturing variable. Component 1 will explain OP2. OP variable, operational performance variable, right? I'm not going to explain how to calculate AVE value since we did this last time. If you want to do that, just send me a message. I can do that part. To explain the moderation analysis result, I'm going to part, right? But if we get enough time later on, I will explain again to you how to calculate the AVE value. Right? But this is your final result. So average. So by looking at these loadings, you can say these two factors are almost separated, and we can now calculate the factor scores, and also you can check the reliability. Here you got 3 variables, LM3, 5, 6 into first factor, right? Remember these 3, and then to analyze in scale, reliability, right? Analyze, scale, reliability. What are the variables now you got? LM3, LM5, LM6. Your convex alpha value is 0.754, 754, right? Which is less, which is greater than 0.7. So reliability is confirmed. Do the analysis again for the OP variables. What are the OP variables we have here? OP2, 3, 4, 5. Convex alpha value is 0.815. Therefore, reliability is also okay, right? Reliability is okay. To confirm the convergent validity, you need to calculate the AVE value only, right? I think we did the same calculation for the same set of variables last time. So I think you already made the calculation again. I can do that later, right? Now you can calculate OP variables and OP variable and NP variables here, right? To do that, go to transform compute, sorry, not transform. Here you have the factor analysis. No? Go back to factor analysis. Factor analysis, only thing you have to do is you of the factors. Click on this scores. Here you will get an option to save the variable, save the factors as variable. Click on this. Click OK. Now you got two, factor 1, factor 2. Factor 1 score, you need to identify what is this factor 1, what according to our analysis, factor 1 is, factor 1 has higher loadings, so OP variables. Therefore, we need to name factor 1 as OP. Then factor 2 is LM. In the label also do the same change. OP is the first factor, second factor is LM. Because you got higher loadings for the second factor in LM variables. Higher loadings are higher loadings for the second factor for the LM variables. Therefore, LM is the second factor, OP is the first factor. Now this is OP and this is LM. Here you have the size, right? I will change the size. It's better you change this name as organization size. Right? Because these variables will be displayed in your outputs, right? So now you have to do the moderation analysis. How can we start the moderation analysis? Here you don't have to standardize values, right? Because you are using factor scores, and your dependent variable is OP according to the research model. Dependent variable is organization operational performance. Lean manufacturing is the independent variable. Firm size is the moderator variable. So we start with the predictor variable only. We don't use the firm size. So we include firm size, but we don't include the interaction effect, right? Now include the two variables, lean manufacturing and organization side in your regression analysis first. Go to analyze, regression, linear. Dependent variable is operational performance. Independent variable is lean manufacturing, and also the categorical variable representing organization size. Here we got this result. according to the analysis, ASCA is very low value, and however, there is significant relationship between these variables. And if you go to the coefficients table, you can see LN variable has a significant relationship with operational performance, but not the organization size. Not the organization size, right? But we don't know whether these two will have interaction effect, right? So you have to include the interaction effect into the analysis now. Now, before including that, you have to multiply these two variables, organization size and lean manufacturing, to calculate the calculate the interaction effect. To do that, I'm going to go to compute variables. Compute variables. Now I'm including int for the interaction effect. Interaction effect means lean manufacturing multiplied by organization size. Here you got the interaction effect variable. This is the interaction. Right? So now you can include the interaction effect as well. Go to linear regression. First, you need to include lean manufacturing and organization size, right? And next stage, I'm going to include the interaction effect to see whether there is significant ASCA improvement. Sorry, I didn't got the ASCA change, right? Go to statistics and get the ASCA change as well. When you include the interaction effect, you got some increase in the ASCA. It is only 4% increase, and but that difference is significant. That difference is significant. If you go to the detailed analysis, you can see lean manufacturing practices is significant. Its p-value is now little bit larger than 0.05, right? But organization size has no direct relationship. That means performance is not significantly different across organization sizes, but interaction effect is highly significant. Interaction effect is highly significant. So what is your conclusion? What is your conclusion? What can you say about this moderation? Is there a significant moderation? Interaction term is significant, right? Interaction term has a small p-value. That means interaction term is significant. But lean manufacturing practices earlier, without the moderator, lean manufacturing has a earlier one also we didn't. Now, yes, with the organization size and lean manufacturing only, we had a very good impact from lean, right? Significant impact of lean. But here, in our final analysis, including the moderator, we got very little impact of lean manufacturing. Actually, its p-value is larger than alpha. That means if your alpha is 0.05, now it is not significant. Or sometimes we say it is marginally significant when you increase the alpha up to 10%, it is marginally it is significant. But this is a situation like complete moderation, right? If alpha is 0.05, this lean manufacturing is no longer significant, but its interaction effect is significant. This is a complete moderation situation. Complete moderation, or at least high moderation effect, right? High moderation effect, because lean manufacturing practices direct effect is extremely low compared to previous one, right? But interaction effect is significant, and also interaction effect has a positive beta coefficient, but still we can't say that it is positive. I mean, compared our zero categories, medium organizations, one is large category organizations that we can say in large category organizations, the relationship between lean manufacturing and lean manufacturing and operational performance is larger. But that is only the indication. But according to your hypothesis, you can only say that organization relationship between lean manufacturing and operational performance varies across organization sizes. That's all, right? But you can identify that this relationship is stronger for larger organizations, right? There is some indication because you got positive coefficient, right? You can recommend for future studies to study whether there is a stronger effect of lean manufacturing in large organizations compared to small or medium organizations, right? You can recommend that kind of thing for the future researchers. But here you have identified that there is a significant moderation of organization size. Did you understand the whole analysis? Any questions?
I think it's very clear now, Dr. Chatra. Yes.
Okay. So it's better you do the assumption check point of including interaction effect separately. You can simply include the interaction effect together because you check the R-square value change, and also you can go to the plots, obtain the error plots to check the assumptions. That is also important after fitting the regression model and getting results, hypothesis test results. You can prove the assumptions are valid, then your analysis is okay. It is actually your model is model is valid, right? It's a valid regression model. So you can include this residual here. Standardized residuals are going to be in y-axis and predicted values are going to be in the x-axis. And also you can obtain the histogram of residuals and normal probability plot of residuals. Here you can see normal probability histogram of residuals as no serious issue, but there are some large residuals that's kind of okay. And normal probability plot is not, this should not be exactly normal, but some level of normality is there. Most of the points lie on the straight line, and there is no issue in the homoscedasticity assumption of the errors, right? We don't see any particular pattern in the error plots, right? So it is also better, it is better to include the error plots as well in your appendices at least, right? So that the reader get better confidence about your results. So I think in that example, you understood clearly how to check the categorical moderator, how to check a categorical moderator. Right? Now I am going to do another example with a continuous moderator, right? With a continuous moderator. And also, same in the data set also, you could see the difference between the two organization sizes. If you did the analysis separately, lean manufacturing and operational performance regression separately to both groups. I mean, organization, if you divide the two groups into two, then you can do the regression analysis again between these two, this way, right? To do that, actually, you have to divide the whole data set based on the organization size. I will explain that as well. Data, split file, compare group based on organization size. Then you compare the regression result. Now I'm going to do the regression analysis again. Between lean manufacturing and operational performance, no need to include the organization size now. And also I'm not going to get any error plot, right? I just want to show you how to get the group comparison in moderator analysis, right? median group regression result is not very significant, but large groups it's significant, right? This is a very good indication of the moderation, right? That means the relationship between lean manufacturing and operational performance exists in large organizations only, right? This has very small relationship when it comes to medium scale group, right? And also, if you compare the beta coefficient of standardized coefficient in the large group is 0.194, which is marginally significant. That means if your alpha is 10%, this is going to be some significance. But when it is compared with the large group, it has 0.6 beta coefficient. 0.6 is very large compared to medium group. That means a positive relationship is there in the large group, right? And this is also another indication of moderation. Here you can see high significance is there in the large group, but no significance, so only marginal significance in the medium scale group, right? That means the organization size moderates the relationship between lean manufacturing and operational performance. Both of these things are possible, right? Even though you are doing the analysis by including the interaction effect, which is the right method, right? Including the interaction term is the correct method. To visualize the result, to show the reader the difference between two groups, you can use this regression and compare the two coefficients. That would be good to interpret your result. That would be better to show the result, visualize the result. Okay. Now I'm moving to the last example. Look at this data set, this research model. Test the following research model using the data in job performance moderator. Right? There is a relationship between knowledge and satisfaction, and education is your moderator variable. And what are the hypotheses? Knowledge has a positive impact on job satisfaction. Positive impact is our relationship, right? Actually, we are here checking the relationship between knowledge and satisfaction of managers, right? When they have good knowledge, are they satisfied with their job? H2 is education level moderates the relationship between knowledge and job satisfaction of managers, right? Education level moderates the relationship with the higher levels of education, which has some different kind of relationship. However, here we have not hypothesized any positive or negative moderation. Education level moderates the relationship. We haven't said that education level positively moderate the relationship between knowledge or negatively moderate. If you have enough literature evidence to do that, please include that. Right? If you have some indication that knowledge has more effect on satisfaction when people are more educated or not, right? Weaker or stronger relationship can be hypothesized. You can open this data set, job performance moderator. Is the data set. But here you don't have factors, you have to create the factors for education, knowledge, and satisfaction. So let's do the factor analysis first. Analyze dimension reduction factor. I'm going to include all the three factors. Education is also here. Education level. Education of people has not been measured as a categorical variable, but as a continuous set of variables. Education 1, 2, 3, up to 5, right? That means they have actually used several indicators to check the level of education of people, not just their education qualification, right? Maybe they have checked some other indicators as well, right? So include all the variables together and go to the rotation. Rotation is Promax, extraction is principal component. Click OK, and but you can also get the factors, factor loadings, suppress some factor loadings, suppress small coefficient below 0.3 is better. You got three factors, which is our expectation, but let's see what is the pattern. Knowledge, all the knowledge variables are loaded into third factor. All the satisfaction variables are loaded into the second factor. All the education variables are loaded into the third factor. And also their loadings are very high, larger than 0.7. Right? Larger than 0.7 means very good. And all the loadings which are not shown here should be less than 0.3 because we suppress the loadings lower than 0.3 only. Therefore, there will be significant difference between the not shown factor loadings and these factor loadings. So you can clearly confirm the discriminant validity. You can clearly confirm the discriminant validity. And also you can calculate the AVE to confirm the convergent validity as well. Right? But I'm not going to do that calculation now. If you get enough time, I can again show you how to do the calculation. But I would like to calculate the reliability coefficients. Go to reliability analysis. This is how you have to get the reliability analysis, analyze, scale reliability. Include all the knowledge variables together and calculate the Cronbach alpha value 0.835. Is 0.835. And I'm going to remove these variables and include satisfaction variables. There are only 3. Luckily, we got very good result at the first step. Otherwise, if you could have, if you remove some of the variables, we will end up with not sufficient number of variables because you have collected data only on 3 indicators for knowledge, 3 indicators on satisfaction, which is not that much good, right? It is better to collect data at least for 5 or 6 indicators, right? And do the reliability analysis again for the education variables. This Cronbach alpha, both Cronbach alpha values are larger than 0.7. Let's see the Cronbach alpha value for the education variables, which is also larger than 0.7. With that value is 0.869. So there is no reliability issue, no validity issue. Still, you cannot say anything about the convergent validity, but you have to check that, right? Right? I confirm on the reliability and discriminant validity. Now I am going to calculate the factor scores. Before calculating it, you need to identify what are the variables, what are the factors. First factor is going to be education. Education. Second factor is satisfaction. Third factor is knowledge, right? And also I forgot one thing. It is very important to do when you are doing the factor analysis. It is also good to get the KMO, test statistic, and Bartlett test CSCT to check the sufficient correlation between variables to run a factor analysis. And also I'm going to store the results, scores as variables. Here we got the KMO result. KMO value is 0.816, which is very good. And Bartlett test CSCT value, P value is also larger than 0.05. That means Bartlett test is significant. This indicates that the data set has sufficient variability to run a factor analysis, right? Otherwise, factor analysis is not a good method. If your case KMO test statistic is very low, below 0.5, below 0.6, then your factor analysis would not be the suitable method to do this analysis, right? That is the only thing you can interpret from this value. And also you have got very high variability explained by the 3 factors, which is also good, right? Now you have all the 3 variables. Remember, first factor is education. Second factor is satisfaction. Third factor is knowledge. So I'm going to name the factors now. First factor is education. I'm going to name that factor as education and label is also education. Second factor is satisfaction. We identified these things from our pattern matrix. Second factor had a large load, had large loadings for satisfaction variables. Third factor is knowledge. Factor 3 is knowledge. Factor 3 is knowledge, right? So these are the 3 factors. Now you can do the regression, and remember your research model. The way you have to conduct the analysis depends on the research model. Your predictor variable is knowledge. So most important variable, first variable you are going to include in your model is knowledge. But you have to include education as well. But you are not going to include the interaction effect, right? Actually, you need to calculate the interaction effect as well. Before going to do that, I would like to check these 2 variables first, right? Only these 2. So go to regression analysis, linear regression. Dependent variable is satisfaction. Independent variable is knowledge and education. Here you can see the overall regression is significant. Its R-square value is around 36%, right? And overall regression is significant. That means at least one X variable is significant. Here you got the result of both variables. Knowledge and both knowledge and education are significantly related to the satisfaction, right? As you suggested, knowledge has a positive relationship with satisfaction, right? That means knowledge, when people get more knowledge, they are satisfied about their job, right? Because they may be feeling confident in their job, right? So there is a significant positive relationship between knowledge and satisfaction. However, we don't know whether this relationship will not be there when there is an interaction term, right? So you need to check the interaction effect now. Before doing that, you need to calculate the interaction effect, right? Go back to calculation, transform, compute variables. I'm going to include the interaction effect int. Numerical expression is predictor variable, that is knowledge. Double click on the knowledge variable and put the asterisk sign, then include the education variable, right? Knowledge times education will be included into the interaction column. Go back to the data set and see the variable. This is the interaction column, right? So now you're going to include the interaction term. So at the first stage, I'm going to include the interaction term separately to see the R-square change. Linear regression, include the dependent variable first, independent variable knowledge and education. In the next stage, click on next, include the interaction term. And also our interest is to see the interaction significant R-square change. Click on continue, click OK. Look at this. R-square change is 0.004, which is not significant change. From this stage, actually, you can guess there is no moderation. There is no moderation, right? Because this R-square, after adding the interaction effect, R-square is not significant. R-square increase is not significant. If you go to the last model, you can clearly see that. Knowledge has positive relationship. Knowledge is significant variable. Education is also significant, but interaction effect is not significant. So what is your conclusion? Which hypothesis is supported, which hypothesis is not supported? H1 is supported. Knowledge was a significant, knowledge got a small p-value, right? So knowledge has a positive relationship between, knowledge has positive effect on satisfaction. That means H1, hypothesis 1 is supported, but not hypothesis 2 related to interaction effect, right? Here, to check this effect, actually you are checking the relation, third coefficient, right? Interaction effect, right? Interaction effect.
Dr. Chaturani.
Yes, sir.
Now then we can take education as another independent variable. No, we can change the conceptual model. Am I correct?
Even though we have not hypothesized that, you can also include that hypothesis if you have enough evidence from literature, or if you are really interested in finding that relationship as well. That means direct effect of education on people's satisfaction. Actually, that is also meaningful, right? In this example, I have not included that, but that could also be a good hypothesis when people get more educated, whether they are satisfied with their job, right? Knowledge is something different. So both variables have significant positive relationship with satisfaction, but there is no interaction effect. That means these two will not have any combined effect on job satisfaction, right? We cannot say that when people are more educated, their knowledge will be more impact. Knowledge will have more impact on their satisfaction. When people are getting more, less educated, they are having less satisfaction on. Knowledge will not increase their satisfaction. That kind of thing you cannot see, right? There is no combined effect, or moderation is in the other way. In other words, moderation effect is combined effect. There is no combined effect of education and knowledge on job satisfaction, but separately they both increase job satisfaction, right? Job knowledge has a positive relationship as well as education. Only thing is we have not written a hypothesis related to education, but you could have done that, right? Okay, that's all about this analysis. If you need to know anything else, please tell me, I can explain that. And also you can check the assumptions as well on the same module. I'm going to include this interaction effect now with the two variables and check the plots. Standardized residuals versus predictor values. Histogram of residual and normal probability plot. You can see approximately normal behavior in errors, but actually it is not a very good normality, right? But it is okay for our this and this. You are not checking exact normality, right? Approximate normality is enough, right? Almost all the error terms between -3 and +3, and there is no serious issue in the error plots. So we can confirm our assumptions of the model as well. Okay, any questions? So every time you deal with indicators, sets of indicators, it is very important to check their reliability and validity first and do the fact analysis. You can actually check the validity and reliability with the exploratory fact analysis as well. But only thing is there are some limitations. You cannot confirm the unidimensionality of the model using exploratory fact analysis. To do that, you have to go with CFA, right? With the confirmatory fact analysis, which is not possible to do with SPSS, but still you can confirm the convergent validity, discriminant validity, and reliability with the fact analysis. Okay.
So if you do not have any questions from the audience, I think we can conclude the session. And so we highly appreciate Dr. Chaturani, your knowledge and sharing your knowledge and your time. Thirenika, you can conclude the session.
Thank you, sir. Good morning, all. Thank you again, Dr. Chaturani, for yet another very informative session. To summarize the contents of the workshop, Dr. Chaturani took us through the theoretical aspect of the regression analysis, types of regression models, model adequacy checking procedure, as well as mediator and moderating analysis was also elaborated. I'm sure it was very valuable workshop series for all the participants, and all the recordings of the previous and today's sessions and relevant material can be referred to from the LMS page of the Research Center. On behalf of the Research Center, I thank Dr. Chaturani again for dedicating almost 8 hours of your valuable time for this workshop series and for sharing your immense knowledge. We hope to collaborate with you again in the future as well, madam. And I also take this opportunity to thank all the participants as well, and hope you will join with us for future workshops as well. Thank you all and have a good day.
Thank you very much, Tirumika and Professor Lalit, for giving me this opportunity to share my knowledge with my faculty members. Thank you very much, you all, for your participation and cooperation throughout the sessions. Thank you.